morning everybody. This is Tuesday the 14th of February and this is the work that you must complete before Friday, and Friday's assessment with C1 and S1, that's a 1 hour paper, and C2 just chapters 1 to 4. So what I'm going to do today is actually within the assessment. So looking back at what we did, we found the midpoint of a line, which was from C1 as well, and we found the distance between a pair of points. We're going to look at, if we go through, that's the first example, so that equation, that formula is not given, you have to memorise it. Show the substitution and then do your calculations. We then did a quick sketch and we know that the diameter and the radius of a circle are related in as much as the diameter is twice the radius and the midpoint of the diameter is the centre of a circle. We then looked on to find the centre. We were given the centre of a circle, which was the midpoint, and then we found out point Q because we're told that PQ was a diameter. Did a few questions from that exercise. Another example on perpendicular lines, which was from C1. Then we looked at a chord and a radius, and the key thing about this is that a chord and a radius always meet at right angles, always. So that's one property that we're going to use today as well. Right, what I've got which is new for you today is from GCSE. So this is work that we're going to cover today. As I had just said before, that we've got a radius here, that's the centre. We've got a radius meeting a chord, and the key thing that you need from this, it's a perpendicular bisector. So it bisects, which means cuts in half. And when we've actually got a line that cuts in half at right angles, it's called a perpendicular bisector. So what we can see here is this radius, or the line from the centre to the chord. It's not quite a radius, it's a bit of a radius. Cuts this chord in half at 90 degrees. And you can see here that that's what's called a perpendicular bisector. Moving on. This is what we've also got from GCSE. We've got the centre of a circle, which is here. We've also got a diameter, and the angle that is supported by a diameter is always 90 degrees. And what we tend to do on this one is we apply Pythagoras Theorem to show that we have got a right angle. So the other circle theorem that we're going to have a look at, that we've done before, and watch out for types of triangles. So in the second diagram we've got a perpendicular bisector, we'd be expected to put that in. But we've also, if we join up lines, we've also got an isosceles triangle. So this may bring in some of Pythagoras' theorem SOHCAHTOA, and we also know that this angle is the same as this one, and that's the same as that. So the angles are bisected at the centre as well. The other thing that we have is an external point to the circle where PA is a tangent. So going from P to A is a tangent, going from P to B is a tangent. We've also got a radius here, and we've got another radius which is BC. A tangent and a radius always meet at 90 degrees. And the other thing that we can put on our diagram is that this line is the same length as this. The radii obviously are the same length. And then if I draw a line in from C to P, I can construct two right angle triangles, and I know that this angle ACP is the same as ACB. And that should all be from GCSE, from your circle theorems. What's new at A level is we've got the centre of a circle. If we have a chord, say on another chord here, if I draw a line from the centre to the chord, or each of them, and it goes right through them, like so. So going through the centre and perpendicular, that obviously means. And we've got another one going from here at right angles. And this one is also at right angles going from the centre. Then the very, very important part here is that both of these lines intersect at the centre of the circle. This might be new to you, but it's certainly used a lot in A level. So that's the centre, and we've got a line going from the centre to each of the chords, so that's a chord there, and we've got a chord here. If that happens, then you know for sure that they both intersect at the centre. Let's apply all of these theorems to the problems that we're going to do with circles in this chapter, and look at the next example. Example 6. The lines AB and CD are chords of a circle. The line y equals 3x minus 11 is the perpendicular bisector. So that's your key statement there, perpendicular bisector, key statement. The line y equals minus x minus 1 is also the perpendicular bisector of CD. Find the coordinates of the centre of the circle. Well, we just looked at that last example, or last circle theorem that was new to A level, and we know that these lines, if they're perpendicular bisectors of chords, then they must meet at the centre of the circle. So let's do a sketch of these lines. The first one, y equals minus x minus 1. If we let y equal 0, then we get x is equal to minus 1, so that's where it cuts the x-axis. And if we let x equal 0, then we get y is equal to minus 1, which is just the y-intercept, which is 0 minus 1. Right, it's a bit close together on the diagram, so it's that point and that point, and then what we need to do is a nice sketch of that line. If you can, you should be using a ruler and a pencil. It's difficult with this package, I can't particularly do it. So label that line y equals minus x minus 1, and then the other line is y equals 3x minus 11. So if we let y equals 0, then 3x is equal to 11, so x is equal to 11 over 3. So that's the point, 11 over 3, 0, and if x is equal to 0, y is equal to minus 11, so that's the point 0 minus 11. Pop that on a diagram, that's this one, 0 minus 11, and 11 and a third is about 11, 3 and 2/3, so it's roughly there. So if we try and sketch through that as well, oops, not a good diagram, try and do it from that way. So we'll see our centre of our circle is going to be in the middle. So what it's looking like is we've got a chord perpendicular bisector of it, which is your y equals minus x minus 1. And then we've got another chord maybe down here, and we've got that as a bisector. So that's our two lines, and they're actually crossing at the centre. So that's the new fact that we need to draw to find the centre. So if it's a point of intersection, we just solve these simultaneously. And it looks like this. So y equals minus x minus 1, we'll call that equation 1, and y equals 3x minus 11, call it example, equation 2. So solve these simultaneously. So I can just make one equal the other. So minus x minus 1 is equal to 3x minus 11. Move them around, so take the 11 to one side, take the minus x to the other. So x is going to be 10 over 4, which is 5 over 2, which can also be equal to 2.5. So we have to find a y coordinate. So if we go into equation 1, y is equal to minus x minus 1. So that's going to be minus 7 over 2, or minus 3.5. So our centre of our circle is going to be 5 over 2 minus 7 over 2. And if we look at a diagram, you can see there 2.5 and minus 3.5. The diagram's quite accurate. So key thing that you need to take from this is the lines which are perpendicular bisectors of chords in a circle intersect at the centre of a circle. That's your one new thing from A-level so far. So what I'd like you to do is exercise 4b. I'd like you to do question 1, 4, 6, 7 and 8. And you'll find that on the next page. So questions 1, 4, 6, 7 and 8. And then if you pause, let yourself do a couple of questions. If you fast forward, the solutions are after this exercise. So pause now, do some of the questions, and then we'll move on. Right, hopefully you've managed those questions, and you can see here, question 1 is a quick sketch there. And we were asked to find the equation of L, so you need a point and a gradient, and you had perpendicular lines. So what we should have had, I'll just move this up slightly, the equation is y equals minus x plus 7. And a sketch is always advisable. Moving on to question 4. We've got a diameter passing a line passing through P and perpendicular, so we're using all the M1, M2 from, if we look at it here, M2 minus M1, M1, and then this equation again, substitute in, and then we should be able to have different forms there. It doesn't look very clear at this point here, so I've rewritten it, and I've multiplied by 3 and put it in the form of ax plus by plus c. Just depends what the question asks you. Okay, moving on to question 6. We have to find out the gradient of mn. Then that allows us to find out the perpendicular gradient. Then we want the midpoint. Then I use this point here and the gradient of minus 4/3. Pop it into the equation from C1. Work your way through, and then you've got it in the form of, it's asked ax plus by plus c. So hopefully you work your way through that. I've done a diagram just at the side there, and it gives you a good idea of what's going on. Right, moving on to question 7. We have AB and CD are chords, and they're perpendicular bisectors. We want the centre of the circle, so that's based on the last example that we did, and we got the centre to be minus 3, 2. And then question 8, done a little diagram as well so you can see what's going on. We've got lines EF and GH, which are chords, and then you've got perpendicular bisectors. You have to work out a few things here, midpoints, equations of line, solve them simultaneously, and then the centre is 8, 0. And that one is typical exam standard, but that's the one new thing that you've got to remember from there, from the A level. Right, let's move on to the next part, and I am only going to briefly look at this because we've done this in C1 before, and all it's doing is using the distance formula, which is just a fancy formula for Pythagoras' theorem. So if we look at the first 2 points that we've got, we want the distance between 2, 3 and 5, 7. Well, if we look at a diagram, all we have actually done, as if you can draw nice straight lines, all you've got is a right angle triangle. So if you apply Pythagoras' theorem, this length is y2 minus y1, and this length here is x2 minus x1. And you square them and add them to get d squared, and then take the square root at the end to find your answer. So for this one here, we've got d is equal to the square root of, I'd always quote the equation because this is not given to you, x2 minus x1 all squared plus y2 minus y1 all squared. Substitute your values in. So we have, doesn't matter which way around you do it as long as you're consistent with your order. So 5 minus 2 all squared plus 7 minus 3 all squared. And that gives you the square root of 9 plus 16. You should recognise that as a 3, 4, 5 triangle. And it's square root of 25, so the length is 5. A little diagram might help if you wanted to just suss out where it was on the coordinate system. And we've got something that looks like this. Again, please use a ruler and a pencil. Label your axes. We've got the point 2, 3 here, and nominally 5, 7 here. We want the length of that line, which is d, so we take it down, form a right angle triangle. So this part here was 3, and this part here was 4, and we worked it out from there. Looking at part B, just a little bit of algebra going on. So same thing again, d is equal to the square root of x2 minus x1 all squared, y2 minus y1 all squared. So d is equal to the square root of, right, we'll take minus 3a minus 4a all squared, plus the y's are going to be 2a minus a all squared. So that's minus 7a all squared plus a all squared. That's the square root of 49a squared plus a squared. So d is equal to square root of 50a squared. Or you could write it as a root 50. And root 50 we can simplify even further as root 25 root 2. So that gives us 5a root 2. And this is where surds can come in as well. As we can see in that final example there, can you give that a go, please? So if you'd work through that, hopefully this is manipulating surds. In C2 you can use your calculator, but you'd be expected to simplify it at this stage here. Right, as I said, we've done this in C1, so we're now going to apply it to actual circle questions. We've got PQ as the diameter of a circle. Find the radius of the circle. Well, you know the relationship between the diameter and the radius. The radius is half the diameter. So if we work out the length of PQ and just half it, then we should have the radius. So we take PQ is equal to the diameter. So half PQ is equal to the radius. So if we work out what PQ is, I'm just going to work it out as squared and take the square root at the end. It just saves me writing the square root sign all the time. Just been a bit efficient really. So PQ squared, we'll put our values in. Minus 1 minus 6, I'll square it all. Put the y values in, 3 plus 3, all squared. So we get PQ squared is equal to 49 plus 36. PQ squared is 85. So PQ is equal to the square root of 85. And that means that the radius is equal to half PQ, which is equal to half root 85. Or we could write it as root 85 over 2, and you'd be expected to simplify that if it could be. Now, one of the reasons that I've left it in terms of squared is because you'll see with the next example, we use Pythagoras' theorem, and Pythagoras' theorem deals with the square on the hypotenuse and the sum of the squares on the other two sides. So let's move on to example 9. We've got the line AB, which is the diameter of a circle, and we've got the points AB. The point C lies on the circumference of the circle. Find the values of AB squared, AC squared and BC squared. Hence, right, so the hence part means that now we've worked out AB squared, so all the lengths of the sides squared, we should be able to apply Pythagoras' theorem. And this is known as the converse of Pythagoras' theorem. I think first of all it might be a good idea to draw a diagram. So if we get an idea of what we're looking at, so it makes a bit more sense. Label your axes, please. Right, we've got B roughly there, which is 7 minus 3. This is totally not to scale, so just watch out. C is 14.4, just over here a bit. So C is 14.4. And we've got A further across to the left, which is minus 3 and 21. Now we're told that AB is a diameter. So if we join that up, there's the diameter. And that means that all of these points, oh, it's a bit of a wonky circle, all of these points, it's a very wonky circle, lie on the circumference. Yeah, that's not great at all. Anyway, it gives you an idea what's going on. If we then join that and that together, that should actually be a right angle. So maybe if C was a little bit further down, then that would look a bit better. Can you draw your diagram a little bit more accurately than mine? That's a bit of a disaster. So AB is the diameter. Let's do AB squared using our formula. So AB squared is equal to 676. Check that, make sure my arithmetic's okay. For AC squared, so for AC squared I get 578, and then for BC squared and that's equal to 98. Therefore, AB squared is equal to AC squared plus BC squared, because 676 is equal to 576 plus 98. Therefore, by Pythagoras' theorem, angle ACB is equal to 90 degrees. But what I'd like you to do now then is, using these facts from the examples, is exercise 4C. I'd like you to do question 4 and question 9. So if you stop the video now, try those two questions, and then when you've finished, the solutions will be before you. Welcome back. Here's question 4, and you're asked to find out the radius. So that's based on the first example, and we just half that, so that's root 10. Just make sure that you can't simplify that any further. We then look at question 9, same sort of thing. Use Pythagoras' theorem, and we showed that angle ABC is 90 degrees. So that angle there is 90 degrees. And then from there we need to work out the area. So if we take AB as the base, and we've got a perpendicular height, or vice versa, it doesn't matter. When you multiply them together, you get 15 units squared. So it's bringing in a lot of GCSE work as well, and hopefully you have remembered that. We're going to move on now to the equation of a circle when the centre is the origin, when the centre is not the origin, when it's got a value of A and B. So if we look here, I'm hoping that you have done this in GCSE, so it should be relatively straightforward. And it's a bit like loci that you've come across before. So if this is a general point on the circumference, which is xy, and we've got a radius there, if we apply Pythagoras' theorem by dropping a perpendicular down there, that's y and that's x. So if we apply Pythagoras' theorem, then that's what we get. X squared plus y squared equals 0. And this describes, because it is a loci as well, it describes the path of xy around the circumference of that circle. So the centre is 0, 0, and the radius is equal to r. Now this equation is not given, therefore can you highlight it and memorise it? It's not in the formula booklet, so learn this. So if I just give you a quick example of this. Say we had x squared plus y squared equals 16, then that means that the centre is 0, 0, and the radius squared is equal to 16, so the radius is actually equal to the square root of 16, and because it's a length we just take the positive value of it, so the radius is equal to 4. Now you may not have come across the next one, which is the centre is AB, so it's actually been moved from the origin up to AB. Now we can do exactly the same thing. We can say that x, y is a general point on the circumference of the circle. So using loci and the centre being AB, what path does it actually trace? Well, we've got the equation underneath there. It's not given to you, so you have to learn this one as well. So let's just see how we arrive at that. Well, again, if I take a horizontal and I drop a perpendicular, I still have a right angle triangle. Now this length here is just y minus b, and this length here is x minus a. So if I apply Pythagoras' theorem, it's simply x minus a all squared plus y minus b all squared is equal to r squared. And then you can see from there that a and b, that's the centre of the circle. And you've got to be careful to match up the signs as well. And the radius is equal to r. So you've got to remember to take the square root of whatever number that you've got on the right hand side. Let's do an example of this to help us out. Just as a reminder, because this equation is not given to you, you should write it first of all and then do any substitutions. So we have got an example. Write down the equation of the circle with centre 5, 7 and radius 4. So we always write the general equation of a circle first. So even if the origin, you're still going to get x squared plus y squared equals r squared. So we write the equation first of all, and then we show a is the x coordinate of the centre, so that's 5, and y is the b part of the equation, so it's minus 7 all squared is equal to 4 squared. Don't forget to square that can be a common mistake. So eventually we get x minus 5 all squared plus y minus 7 all squared is equal to 16. And it must be in this format so that we can read quite easily the centre AB. So what I'd like you to do, if we have a look there, that was A, that was B, and that there was R. So the exercise that I'm looking for you to do is exercise 4D, and that's question 1A, C and E. Now I can't fast forward to the answers just yet, so we'll go through another example. You may want to try this just after this example, or just leave it to the end. So this example now uses the equation, so we've got to compare, so CF is just Latin for compare it to x minus a all squared plus y minus b all squared equals r squared. And what to be very careful of is that the signs match as well. So the signs for b match, but the signs for a don't match, so that means that a is going to be equal to minus 3 and b is going to be equal to 1 and the radius is equal to 4. So what we quote is the centre is minus 3, 1 and the radius is equal to 4. We do exactly the same with the next one. We compare it to our original equation, x minus a all squared, y minus b all squared equals r squared. If we look at the signs, they do actually match, so we can read the value of a and b straight off. So a is equal to 5 over 2 and b is equal to 3 and r is equal to the square root of 32. We should simplify this as much as possible. So we'll say the centre is 5 over 2 and 3. We could say that that's 2.5, and then r is equal to, we'll make that into root 16 root 2. So r is equal to 4 root 2. So simplify as much as possible. So what you should be able to do now is exercise 4D, question 2, A, C and E. You can pause that, can do it, I'll give you the answers later on, but we can get on to the next example. Right, what we need to do is a skill from C1, and that skill being completing the square. So we've got an example here, and it's not in the standard form of x minus a all squared, y minus b all squared, etc. So what we've got to do is gather the x's together, gather the y's together, and then that's plus 3 is equal to 0. And then we apply complete the square on the x bracket and then the y bracket, and we should get it in the standard form. So it looks like x plus 2 all squared. Now the extra part there would be 4, so we've got to take 4 away. And then for the y, we've got y plus 3 all squared, and our extra bit there would be the 3 squared, so that's minus 9. So let's get the final form of it. X plus 2 all squared plus y plus 3 all squared, and on the right hand side that should be 10. So we've got a centre and the signs don't match, so it's going to be a centre of minus 2 minus 3, and a radius is equal to root 10. So you should now be able to do this question here, but this was question 3 part A, but you should be able to do B and C, so practice your completing the square. Moving on, we've got to show that the circle passes through this point. So if we've got to show something, we can't assume it to be true, so we'll take one side, so we'll take the left hand side, and we'll have values of x equals 5 and y equals minus 8, and I'm going to substitute those in. So it's going to be 5 minus 3 all squared plus minus 8, so it's going to be minus 8 plus 4 all squared, so that gives us 2 squared plus minus 4 squared, which is 4 plus 16, which is equals 20, which is what we expected, is equal to the right hand side. Therefore, the circle passes through the point 5 minus 8. So we've got another couple of examples and then do the rest of the exercise. We've got a diameter, which is AB of the circle, and find the equation of the circle. Well, the centre is going to be the midpoint of the diameter, so a quick sketch is helpful here. So if we do the midpoint, and then if we do the half of the radius, then half of the diameter rather, that will give us the radius. So let's do midpoint of AB. We add the x's together and half them. We add the y coordinates together and half them. So the midpoint, which is the centre, is going to be minus 8 plus 4 divided by 2, and 3 plus 7 divided by 2. So the centre of the circle is going to be 2 and 5. So it should be minus 2. Minus 2 and 5. So by drawing an accurate diagram you can get an idea what's going on. So if we use our standard equation, x minus a all squared plus y minus b all squared equals r squared, we can put our x in, so x minus minus 2 all squared plus y minus 5 all squared is equal to r squared. So we've got the first part of it. Part of it is x plus 2 all squared plus y minus 5 all squared. So we've just got to find out what r is. So r is equal to a half of ab. So if we just do ab squared, that's going to be x2 minus x1 all squared plus y2 minus y1 all squared. substitute your values in, and we get x2 is 4 plus the 8 all squared plus the y coordinates is 7 minus 3 all squared. So AB squared is equal to 144 plus 16. So AB squared is equal to 160. So AB is equal to the square root of 160, which is root 16 root 10, which is 4 root 10. Now that's the radius, that's the diameter rather, so the radius is equal to a half of AB, which is equal to 4 root 10 over 2, which is 2 root 10. So we've got to pop that into our equation. And it's r squared, so it's 2 root 10 all squared. Just watch out for that, it's really important. So our final answer becomes x plus 2 all squared plus y minus 5 all squared, and squaring that gives us 4 times 10, so it's 40. So the bit to watch out for is that you find out the radius, but you've actually got to square it, and 2 squared is 4, root 10 squared is 10, so that's where you get your 40. Right, now you could do question 6 following on from that, and then we've got one last example. Example 14. The line touches. Now if it touches, then it's a tangent, and it touches this circle at the point 10, 0. So I've done a sketch or a diagram screenshot of Desmos, and we've also got perpendicular as a keyword, so we're going to use m1, m2 is equal to minus 1. So I'll give you a chance to copy that diagram down, and then we want to work out a few things. So show that the radius P is perpendicular to the line. First thing that I've done from this equation here is I can put in the centre, and we've got a point there. So we've got this line, which is 4x minus 3y minus 40 is equal to 0. It's not very good in that form, so I'm going to rearrange it into the form of y equals mx plus c. So we get y is equal to 4/3 x minus 40 over 3. So if we compare that to y equals mx plus c, then we get the gradient of the line going through P to be 4/3. Now if the line from C to P is perpendicular to the line, the tangent, then that means we're going to have m1, m2 equals minus 1. So let's work out the gradient of CP, which is y2 minus y1 divided by x2 minus x1. So y2 I'll take as 6 minus 0 divided by 2 minus 10, which gives me 6 over minus 8, which is minus, if I divide top by 2 and the bottom by 2, 3/4. So m of P multiplied by m of CP is equal to 4/3 times minus 3 over 4, which is equal to minus 1. Therefore, they are perpendicular. And I think the secret to this is actually drawing a very a sketch of some sort, but try and draw an accurate sketch, and it does help you tremendously. So we should be able to move on, and the questions I would like you. So the questions that I'd like you to do are on exercise 4D, question 1, A-C&E, 2, A-C&E, 3B, 8 and 9. Now I've put this in a different order. So I can't go on to exercise 4D answers until I've done this to do. No, it's alright. I think I have got it in the right order. Just ignore that last statement. Okay, example 15. Find where the circle meets the x-axis. If it meets the x-axis, we have x-axis here and the y. As you know, along the x-axis, y is equal to 0. So that's what we're going to look at when y is equal to 0. So the equation that we have and if we put y equals 0 in there, we get x minus 5 all squared plus 0 minus 4 all squared equals 65. Square a bracket, square the first, double their product, square the last one, and that's going to be plus 16 equals 65. We're going to get a quadratic here, and the number on the end is going to be minus 24. This does factorise, gives us x and x plus 2 minus 12. Therefore, x is equal to minus 2, or x could be equal to 12. And if we look on a diagram, there's your minus 2 and there's your 12. If there was no intersection, so for example the circle was above the x-axis, we would probably get a discriminant, which would be less than 0, and that would tell us there's no intersection. So it's becoming very synoptic with all the work that we've done on geometry with straight lines, but also with quadratics. When we form a quadratic, we can look at the discriminant. Right, I definitely want you to exercise 4D now. There's the solutions to 1, 2, I don't think I've done 3 just yet. We'll check those. So you're going to gather those together, aren't you? Like so. And you're going to get a y squared minus 3y minus the 8. And then complete the square on that, etc, etc. You're going to have to divide through by 2 first of all on this one, because the coefficient has to be 1 for x squared and y squared. And then moving this slide on, I want you to do 6, 8 and 9. And then the solutions are, oh, I did do 3. There's 3, B and C. And then question 6. Pause if you need to. And then looking at 8, that's the diagram for it. Useful to draw the diagram. And then 9, there's your diagram as well. So similar to the examples that we just did. Okay, moving on to the last part now. We have a couple of more examples and then we've finished the whole thing. This must be finished for Friday. So what I've done is, if you can see at the bottom there, I've actually got a diagram of what's going on. We've got the line y equals x plus 5, and we've got a circle here which has a centre 0, 2. So the centre of this circle is at 0, 2. So it's writing down as much information as possible that we've got. So what do we need to do then? We want a point of intersection where the meet is another way of saying intersection, and when lines intersect we solve them simultaneously. So I've just taken 1 and I'll substitute it into 2. So that will give me x squared plus y becomes x plus 5. And that becomes x plus 3 all squared. And then what we need to do is expand the bracket, square the first, double their product, square the last one, take the 29 across, and what we have is a quadratic. So we've got 2x squared plus 6x minus 20 equals 0. To make the numbers a little bit easier, I'll divide through by 2, so x squared plus 3x minus 10, and this does factorise, and it gives you a value x minus 2, x plus 5, so x is equal to 2, or x is equal to minus 5. So that does help us with the x coordinates. We've then got to move on and find the y coordinates. It's like simultaneous equations from C1. So from 1, y is equal to x plus 5. So when x is equal to 2, y is equal to 2 plus 5, so that's the point 7. So that's the point 27. And when x is equal to minus 5, y is equal to minus 5 plus 5, which is equal to 0. So that's the point minus 5, 0. And if we look at the diagram, we can see there the 2 points of intersection, minus 5, 0 and 2, 7. This is what comes into play with the discriminant, because if you think about it, if you've got a circle, as we've got here, we've got 2 points of intersection, so the discriminant would be greater than 0. If it was just touching the circle, so we've just got 1 point there, then we would have the discriminant equal to 0, so that's the same as 2 equal roots. And if we have no intersection at all, then the discriminant would be less than 0. So have a think about that when we come across more examples to show if it touches. So if it touches, the discriminant would be 0, 2 points of intersection, and no intersection. That's the 3 things that we're looking for, and that's what we did with the quadratics back in C1. Okay, we've covered absolutely everything that we need for Friday, so just a reminder, we've got one more here that we can have a look at in terms of does not meet the line. So think about what we said for discriminant from before. So it does not meet the circle. So we've still got to show that there might be some intersection. I've drawn the diagram here for you as well. So if we substitute it in, we get x plus 2 all squared plus y squared, which is x minus 7 all squared, is equal to 33. So square the first bracket, square the second bracket, take the 33 across, and what we do is we generate a quadratic, and then this quadratic we won't be able to solve, but we can actually thoroughly prove it by looking at the discriminant. So we're going to get 2x squared minus 10x, and then plus 20. I'll make the numbers a little bit easier again, so we'll divide through by 2, so we'll get x squared minus 5x plus 10 is equal to 0. Right, let's look at the discriminant. The discriminant is b squared minus 4ac. In this case we have a is equal to 1, b is equal to minus 5, and c is equal to 10. So that tells me that I've got minus 5 squared minus 4 times 1 times 10 So that gives me 25 minus 40, which equals minus 15, which is less than 0. Therefore, there is no intersection. So you can see there from the diagram, it's not necessary to draw the diagram, you can do it algebraically as I have done, but it gives you a good idea that there's absolutely no way that they intersect. So on exercise 4e, if you could do these questions please, 1, 2, 4, 6 and 7, and I'll do the solutions to those later. And the other thing that I'd like you to do is for the Tuesday that we come back, is hand in on file paper. There are 5 exam questions, okay, 5 exam questions to do, and it's using quite a lot of the C1 coordinate geometry that we've come across before. So y equals mx plus c, perpendicular lines, and diagram. Please transfer all the information onto the diagram to make it easy for you. So just a reminder, on Friday you'll have both assessments. This video and all the questions should be finished because circles are going to be on the assessment. If you've got any problems, I will be around Wednesday, Thursday, Friday. I'm out on a course Monday, Tuesday, so that's why I'm not at the lesson today. So do the best you can, and then there's lots of exam papers for you to do as well.